recording now. It's a pleasure to introduce our next speaker, Tony Yu from CNRS and University of Paris Sud. He's going to tell us about secondary fan, theta functions, and moduli of Calabi-Yau pairs.
Thank you, Andrea, for the introduction, and thanks the organizers for the invitation. It's my great pleasure to speak at this conference. The title of my talk is Secondary Fan Theta Functions and the Moduli of Calabi-Yau Pairs. The reference is this joint work with Paul Heck and Sean Keel, and we are also working on higher dimensional generalizations of this story. So yeah, I've put the note of my talk in the chat. Andrea will probably put it again a bit later. So you can just read and back and forth. If you miss something in my talk, you can read as you like. And also, Andrea has give all of us the power to unmute now. And then whenever you have any questions or comments, please just feel free to interrupt me. Okay, here's the plan of my talk. I will start by introducing the moduli space of Calabi-Yau pairs, and then I will describe a generalization of the classical GKZ, Gelfand-Kapronoff-Zelevinsky secondary fan. After that, I will discuss the construction of mirror algebra via counts of non-Archimedean analytic disks. And finally, I will talk about gluing mirror families over the secondary fan. Okay, so first let's start with the moduli space. Motivated by mirror symmetry, we propose the following conjecture regarding the moduli space of so-called smooth polarized Calabi-Yau pairs. So what are they? By smooth polarized Calabi-Yau pairs, we mean this kind of triples. So we have X. X is a connected smooth projective complex variety, and E is anticanonical divisor, lies in the anticanonical class. It's normal crossing divisor with a zero stratum, meaning that has some intersection until a point. And we assume that each piece is smooth. And then theta is an ample divisor not containing any zero stratum of E. So this kind of triples, they are called polarized Calabi-Yau pairs, and we look at their moduli space, and we conjecture that any connected component Q of the moduli space of such triples is unirational. Yeah, so where comes this conjecture from mirror symmetry? And actually, it comes from a more precise form. So actually, we have a more precise form of the conjecture above for the compactified moduli space. So the compactification, it will take us a bit more terminology to describe, and I will do it now. Yeah, so I need to introduce some terminologies to describe the compactification of this moduli space. First, so let's recall some terminologies from birational geometry. A pair X delta consists of a reduced pure dimensional variety X and an effective Q divisor delta. We assume that none of those irreducible components is contained in the singularity of X. Yeah, so maybe let me say why are we doing this. It's because we want to describe the compactification, and if we just think in terms of curves, we know that for smooth curves, the moduli space is not compact, and if we want to compactify, we should introduce nodal singularities. So here we should allow this thing to break, and then when we allow things to break, it becomes like it has many irreducible components. Then we have to be careful about where to put this kind of boundaries. So that's why there is some consideration in birational geometry for this. And next, a Kohler-Shepard-Baron-Alexeev stable pair is a proper semi-log canonical pair x delta such that kx plus delta is ample. So this is exactly this higher dimensional generalization of nodal curves. So here it's pair, so it's higher dimensional generalization of nodal curves with marked points. And it's studied by Kohler-Shepard-Baron-Alexeev, and it's called a stable pair in their sense. And so this nodal condition in the higher dimensional case, it's more complicated. It's called the semi-log canonical. And and a Calabi-Yau pair is a proper semi-log canonical pair where we ask this sum kx plus delta to be q-rationally equivalent to 0. So Calabi-Yau is a 0 as usual, and stable is ample. So now we want to study moduli space. What we really want to study is moduli space of Calabi-Yau, but in order to compactify moduli space, we'd better have some polarization. Then what we do is to consider this notion of polarized Calabi-Yau pair, which is a triple. It's just Calabi-Yau plus a polarization. So it's a triple xe theta, where xe is a Calabi-Yau pair, and theta is our polarization. So theta is an ample divisor not containing any semi-log canonical center of xe. Why do we do that? Because we want to use this theory of stable pairs, and we'd better not consider arbitrary ample divisor. So we ask the ample divisor not to contain some bad locus, and this is equivalent to asking that when we consider the pair x comma e plus a sufficiently small multiple of this ample divisor, then it's a stable pair. Okay, so it's just some review of terminology from birational geometry in order to describe our moduli space. Now we can use this. So if you are not familiar with this, you can really think everything as a generalization of nodal curves. Okay, so now for sufficiently small positive epsilon, and if we take this pair x comma e plus a sufficiently small multiple of theta, then our moduli space Q of this smooth polarized Calabi-Yau pairs, these triples xe theta, it just immerses into the moduli space of stable pairs, which we denote by SP. And as I just was repeating that stable pairs, it's really a generalization of stable curves. Then its moduli space is really a generalization of MGN bar, of the moduli space of stable pointed curves. So now our moduli space embeds there, and it's proven, I think quite recent, by Alexeev and Heiken, McKernan, and Xu, and that this moduli space has proper connected components. So it really analogous to this MGM bar. This is actually every connected component is proper. Then since our moduli space embeds there, we get a natural compactification of our moduli space, and we denote this compactification by Q bar. So now we can state the real form of our conjecture. The precise form is that this compactified moduli space Q bar admits a finite cover by a complete toric variety. maybe let me make a few remarks. First is that such moduli space of stable pairs, it's an active research field in birational geometry, and there are many recent results for this moduli space, such as like properness, finite type, all these basic properties, but they are usually quite very abstract, and it's difficult to really understand specific examples of such moduli space. So we don't really have much geometric idea for what they are. And they are also can be really singular. So here, our conjecture is really motivated by considerations from mirror symmetry, and also we checked some basic cases also. It's really motivated by mirror symmetry, and it's far from obvious from birational geometry. I'm not totally confident that the conjecture is true in full generality. Maybe we also need to modify it a little bit. Yeah, and so as I said, from birational geometry, there's not much reason that it has anything to do with toric variety. So if you have, are there any questions at this point? Yeah. So let me go on. So with Paul and Hacking, we verified our conjecture in the two-dimensional case. We checked that it works when X is a Del-Petzel surface, and E is an anticanonical cycle of -1 curves, and the theta also is anticanonical. So in this case, we can construct the moduli space by mirror symmetry considerations, and we can check all the properties, especially this semi-log canonical property. And yeah, that's the most difficult part. So the proof of the theorem is based on two things, or in other words, our conjectural idea, our idea for studying the conjecture consists of two things. First is that we want to construct the toric variety. So we are guessing that the compactified moduli space is some kind of quotient of a toric variety. We'd better first construct this toric variety. So we guess that the construction of the toric variety can be made using ideas from Mori theory and Berkovich geometry. That's for the base. And when we have the base, when we have this toric variety and we want to have like a map to the moduli space, we should construct a family over our toric variety, or the pullback family by the map. And for the construction of the family of triples over this toric variety, we constructed as proj of a sheaf of graded algebras with a canonical basis. And the structure constants of these algebras, they are given by counts of non-Archimedean analytic disks. And this is actually a generalization of the mirror algebra construction in my previous work with Sean. So that's the main 2 points of our idea for studying this conjecture. So first point is what is the base? And Second is how to construct the family over the base. Now let me describe a little bit more detail for the construction of the base and the family. So first, what do we do with the base? Okay, yeah, and we do the following. So it's now it's all ideas, not totally precise. Yeah, so how do we find the base? When we want to construct the base, we start with the mirror pair, YD. Maybe you ask, what does it mean? So when we know in specific cases, for example, in the two-dimensional Del-Petzo case, we know mirror symmetry very well, and we can work everything out. Otherwise, it's more complicated. So but here it's just heuristics. So we start with the mirror pair YD, and we assume it has a smooth affine interior, and it's Fano. And we assume also it's normal crossing. So then we consider the canonical bundle K over Y, and we contract the zero section of the canonical bundle. So just we have a mirror, which we assume to be Fano. We consider the canonical bundle, and we contract the zero section. And then we will construct a complete fan, which we denote by sec K over K bar, supported on the Picard. So the Picard group of this K over K bar, relative Picard, and we just consider the real vector space. Yeah, so like this will be the co-character lattice of the toric variety that we will construct. It will be just this Picard, and this Picard is actually just isomorphic to Picard of Y, and we call it the secondary fan of YD. Yeah. So first step, we are saying that this base T of our family, conjectural family, as a toric variety, its co-character lattice is given by Picard of the mirror. So we call it a secondary fan for YD because it's actually a generalization of the Gelfand-Kapranov-Zelevinsky secondary fan for reflexive polytopes in classical toric geometry. That's why we call it secondary fan. And now we generalize it to this much more general case, Fano with pair of Fano and some normal crossing divisor. And it is by construction, we will construct it as a coarsening of so-called Mori fan for this K over K bar. I will recall what is Mori fan. It's defined using Mori equivalence relation for divisors. I will recall it in a moment. And as I have been saying, all this, so the reason we construct this secondary fan is that we conjecture that the toric variety associated to the secondary fan should just be the base toric variety for our family of triples. So it is this toric variety which will cover this compactified moduli space. So in the case of Del-Petzo surfaces, we can really describe very explicitly what is going on. It's just some quotient by some finite group. for the cover. Okay, and yeah, so by this secondary fan construction, we have the base, and now we need to build the family of triples xe theta. In other words, our family of these polarized Calabi-Yau pairs over this base. For this, we start with. For this, we first start with the affine mirror family from the following theorem. As I said, this construction of the family is a generalization of what I did with Shankyo previously. So previously, we had a construction for the affine. For the affine case, it's in this so-called Frobenius structure theorem. Let me briefly recall what is this. What is this construction of the affine mirror family there? So the mirror family, the base of the mirror family in that case, it's just R. It's a spec R, and R is just the monoid ring over the cone of curves. So it's just like a bookkeeping for all the curve classes. And then the family is described by some algebra A. So in the beginning, without algebra structure, A is just a free R module with basis in SKUZ. It's called integer points in the essential skeleton of U. So in other words, we have an explicit description. It's just zero union multiples of so-called essential divisorial valuations on the function field. Essential divisorial valuation means that it's given by some divisor where the volume form has a pole. So then we have a non-degenerate multilinear form on A given by counts of rational curves in U called the Frobenius form. I'm not giving the details here. It's because I talked about it in many other places. But it's also very simple. Just you can imagine one count some rational curves and with boundary condition prescribed by this kind of multiples of these divisors, and one get a multilinear form. And we prove that there exists a unique finitely generated commutative associative R algebra structure on A compatible with the Frobenius form. And this algebra structure is given by counts of non-Archimedean analytic disks in the analytic space. I will give more details later. So anyway, I'm just saying that we have some mirror algebra construction. When we take spec, we get the affine mirror family. And we prove that it is a flat family of affine varieties of the same dimension as U. Each fiber is Gorenstein semi-log canonical and has trivial canonical bundle. So this semi-log canonical, I recall, it's really the condition that we need for this KSBA moduli space. And we can check that the generic fiber is nice. It's log Calabi-Yau and log canonical. So this semi-log canonical or log canonical or terminal log terminal, these are conditions of singularities that appear in the minimal model program, and they are really the correct notions for the compactification of the moduli space. Okay, yeah, here I'm just recalling that we have some construction already for the affine family. Now we want to compactify it, both at the level of fibers and also at the level of base. We want to compactify it to a family of these polarized log Calabi-Yau pairs. So first, maybe you are confused about the base. Here the base is this Z of NEYZ, and before we are talking about some toric variety. So actually they are really close, because the dual of this cone of curves is just the Neff cone. And then when we take the spec R, the base is just the toric variety associated to the Neff cone. And just now, we want the base to be the toric variety associated to the secondary fan. And here we have a cone, Neff cone. So somehow we just want to extend. I mean, we already have something over the Neff cone. We want to extend it to the complete fan. So we prove that this extension is actually possible. We prove that the affine mirror family, that V to the toric variety associated to the Neff cone from the Frobenius structure theorem actually compactifies. So first it compactifies fiber-wise and extends to a family of Calabi-Yau pairs. Like this XE over this complete toric variety associated to this complete fan, we call secondary fan. So we can fiber-wise compactify and then extend to some complete toric variety. And furthermore, we also have polarization. We have an ample divisor, theta. We also have an ample divisor. So ideally, we just want a family of polarized Calabi-Yau pairs. But here, first, we prove that now the generic fiber is okay. Ideally, we wanted all the fibers to be okay. But in the theorem, we prove that the generic fiber is now a polarized Calabi-Yau pair. In other words, when we consider the pair X, E plus a sufficiently small multiple of theta, it's now a stable pair. And yeah, we definitely conjecture that it must work for all the fibers. But the singularities, they are just so complicated to study here in general. And currently, we can only prove it for dimension 2. The reason is that in dimension 2, we have very explicit description of all these singularities, like log. We have classification of these singularities, so we can check by hand. In higher dimensions, we must invent some new machineries, technologies, maybe to study this. Yeah. So as I said, in dimension 2, we can make things very explicit, and we can really get very detailed descriptions of what is happening there. Here is all we can get in dimension 2. Let me just go over this result. So in the 2-dimensional case, we assume Y to be smooth Del Petro surface. Then this family, it's a flat family of Calabi-Yau pairs, the family we construct. I guess this is just what we already have in all dimensions. We get a family of Calabi-Yau pairs. What we don't have in all dimensions is for the is for this polarization. And then for the boundary E, we can just compute that it's actually so simple. It's just a trivial family of cycles. So it's really just like del Petrol surface with a cycle of rational curves. This is family we obtain. And so in general, since it's compactified moduli space, many fibers are just broken into many pieces. As I said, like to compactify moduli space of curves, we must allow the curves to break. Here, the surfaces. So this it's like a two-dimensional generalization of this MGN bar. And in the surface case, most of the surface, they just break. But over the structure torus of our toric variety, they are not broken. They are actually quite nice. We can show that every fiber over the structural torus of our toric base is a del. So for every fiber Xe, X is a del Petrol surface with at worst Duval singularities. Duval is the same, it just means canonical singularity in 2 dimensions. Yeah, so it's nice, just del Petrol surface with Duval singularities. And E is an anticanonical cycle of -1 curves. We are a bit careful to say, we don't say -1, we say kx. It's -1 with respect to kx. It's because when we have singularities, we have to be careful about intersection numbers. But just you can just think of as -1 curves. And then we can compute the self-intersection number of kx. It's interesting because by definition, it's the degree of the del Petrol surface, and this degree is equal to the number of irreducible components of D. Yeah, so the third point says that for our family, in this case, although it's the base is compact, we have many broken pieces, but over the open torus of the base, it's pretty nice. It's just del Petrol with at worst Duval singularities. And in general, they are unavoidable, these singularities. We know that they exist. And then for polarization, in the 2-dimensional case, we can show that it works. So when we add a small amount of polarization, we get a family of stable pairs. And it's really, so then equivalently, we obtain this family of polarized Calabi-Yau pairs. And finally, verifying our conjecture, we show that now we get the induced map because we have our family of we have our family of stable pairs, and it maps to the moduli space of stable pairs, and we show that it is a finite map. Yeah, so in the 2-dimensional case, we have this very explicit description of everything. Then, as a corollary, as I said, in the 2-dimensional case, the mirror symmetry is particularly easy. Actually, it's what people call self-mirror. So that also saves us the extra step of doing mirror symmetry here. Because a priori, we should, in order to study the moduli space of the variety, we should do the construction out of its mirror. But now in the 2-dimensional case, we only need to do once, while in general we'd better do twice. So in the 2-dimensional case, we can show that when we have Y, smooth complex Del-Petal surface, and D, any anticanonical cycle of -1 curves, then the generic fiber of the mirror family is smooth, and actually we just get back the original Y. So somehow, to say very vaguely, like the mirror of Y is itself. So in the mirror family, we find the original Y, and then the image of this finite map above, it's just the compactification Q bar that we were considering before, this KSBA compactification. So in this way, we get we verify our conjecture in this case as a corollary of this explicit description. Yeah. So these are the main results. And now let me talk about more details of some of our constructions. First, I would like to say something about, so as I have been saying, our construction or our idea mainly consists of 2 parts. First is construction of the base, and the second is construction of the family over the base. So for the construction of the base, which is a toric variety, it's really about the construction of some fan. And this is the generalization of this GKZ secondary fan that I will be talking about. Here is our setup for this generalization of GKZ secondary fan. We have V, smooth log Calabi-Yau, K, V in K, some normal partial compactification, and we fix some regular proper map Q from K to K bar. And we assume that K to K bar is so-called relative Mori dream space. I will explain it in a moment. So it's just smooth Calabi-Yau partial compactification and then some proper map, contracting something. In our application, we will apply this setup as follows. We have mirror funnel YD. We take U, the interior, and the K will be the canonical bundle. V will be the interior, will be K minus the 0 section restricted to U. So it's just this GM bundle over U. And Q is the contraction of the 0 section. This is how we will apply. But all we need is just Calabi-Yau, some partial compactification, and contracting something, which is so-called Mori dream space. Idea of Mori dream space is that it is a projective variety such that Mori equivalence of line bundles gives rise to a finite polyhedral fan called Mori fan supported on the effective cone inside the Picard, the Picard group. I will recall what is Mori equivalence. And in general, the Mori equivalence just gives arbitrary like equivalence relation in the Picard group, and Mori dream space is the situation where it gives a polyhedral fan. As a consequence, the minimal model program becomes particularly simple for Mori dream space. We can really look at like how the flops they are happening in the minimal model program from this polyhedral fan. So let me recall what is the Mori equivalence relation of line bundles. Whenever we have line bundle, we can look at its section ring. it's a direct sum of just sections of powers of the line bundle. If the section ring is finitely generated, we obtain a birational contraction from X to the proj of this section ring. And we say that two line bundles with finitely generated section rings are called Mori equivalent if they give rise to the same birational contractions, and furthermore, they have the same stable base divisors. So we want to look at not only the birational contraction, but also we want the base divisors to be the same. Otherwise, if there is some base divisor which differ, we still consider them to be different. And under this equivalence relation, as I said, we may get some very complicated thing in Picard. If we use this equivalent relation, we will get a priori complicated like partition of this Picard. But a particularly nice case called Mori dream space is that the partition we get is actually a polyhedral fan. So some two divisors are Mori equivalent if and only if they lie in the interior of a same cone of the fan. Easy consequence of the definition is that each maximal cone of this Mori fan is just of the form pullback of the Neff cone plus the subcone spanned by exceptional effective divisors for some birational contraction x to x prime. We just apply the definition and we add up this kind of stable base divisors. And next, we introduce a notation of so-called moving fan, which is the restriction of the Mori fan to the moving cone, consisting of moving divisors. So that's a smaller cone in the effective cone, consisting of moving divisors, which are divisors without stable base components. So for these divisors, we don't have this to worry about. Then they are Mori equivalent if and only if they just give rise to the same contraction. And the maximum cones of the moving fan, then they are just pullback of Neff cone of x prime for any contraction which is small. We call such things SQM. It's just it stands for small q factorial modification. Q factorial is a technical condition one has to put to make things work. And other maximal cones are called bogus cones. Okay, yeah, so all this part is a classical story in birational geometry. So now we observe that in the toric case, when YD is toric and when we consider the Mori fan defined as above of this relative maybe I should say that it's as a consequence of the work by Bikar BCHM on minimal model program, when we have Fano in our situation, we get Mori dream space. Okay, so we can apply this. Then we observe that in the toric case, this Mori fan seems very complicated. It's actually isomorphic to the combinatorial construction by Gelfand, Kapranov, Zelvinsky, this GKZ secondary fan. So this is how this GKZ secondary fan comes into the game here, because one can show by some GIT theory that this GKZ fan is actually isomorphic to this Mori fan from this birational geometric description. Then we may guess that let's just use this fan or the toric variety associated to this fan as the base for our family. But in general, we observe that the toric variety associated to the Mori fan is not really the right base for our mirror family. So we study from examples that when we consider this map, when we construct some family over this toric variety and study the map to this moduli space of stable pairs, we don't get a finite map. And so somehow there is some redundancy in the family over this space. And in order to remedy this redundancy, we would like to contract like all the subvarieties over which the family is trivial. And yeah, and it turned out to be really, it's quite surprising that it turned out that all we need to contract are stratas, are toric stratas. So the only things that cause us trouble, they are toric stratas of the toric variety. And all we want to do is just to contract the strata of this toric variety associated to the Mori fan on which the extended mirror family is trivial. But in order to figure out what are exactly these stratas over which the family is trivial, we need to use some ideas from Berkovich geometry. I will explain what we do here. So contracting the strata is the same as coarsening of the fan. So in toric geometry, when we refine the fan, we are doing some blow up. Now we want to blow down something, and it's a coarsening of the fan. So in other words, we want to say what are the cones that we want to glue to get a coarser fan. And we will specify what we glue using some Berkovich geometry, and then the coarsening, it will be our secondary fan. So for this purpose, we will consider the universal torsor over K, and by definition, universal torsor is just the relative spec of direct sum of line bundles. And we observe that the restriction of the universal torsor to V is log Calabi-Yau inside K is again log Calabi-Yau. Then we get a map of so-called essential skeletons of these spaces. And these are really features of Berkovich geometry. So here, maybe you are worrying that what Berkovich geometry is happening here, because like we are not doing some non-Archimedean geometry here. And actually, all we do here is that we have some field. We can just think of complex field, complex numbers. And when we mean Berkovich geometry, we are considering the analytification of the variety with respect to the trivial valuation on our field. And then we get this analytic space, and the skeletons, they are subsets of the analytic space. So when we have these maps between these log Calabi-Yau, we also get the map between the essential skeletons. They are some polyhedral subsets of the Berkovich space associated to our variety. And this map admits a canonical section. I will explain it very quickly right away. So this is the thing we will use to specify what are the cones that we glue, this canonical section. And we glue maximal cones of the moving fan of K for which the associated section phi coincide. And so in the beginning, we just glue the moving part of the fan. And if you remember, they are given by these small birational modifications. So when we do birational modification, we will be getting different sections, and some of them coincide. For those who coincide, we just glue them to a bigger cone. And then this will also induces a gluing of outside the moving part, and then eventually it will be the secondary fan. This is the rough idea, and the main mystery is about this construction of the section. And actually, this section can be constructed in total generality in analytic geometry. So I have written a paragraph here, how this section is constructed. It works in total generality for so-called formal schemes and any flat surjective map with geometrically integral fibers. Let's just skip this. The idea is just that it's a totally general construction, and when we apply to the case of trivial valuation, we get this section we want. And now we should compare the section phi for different birational modifications, k to k prime. So what do we do here? Recall, there is something to be careful because you know, under this birational modification, the Picard group will change. So one has to be a little bit careful. The Picard group will scale a little bit, but let's ignore this. And we recall that we have universal torsor, and we get map between skeleton and then here we are being a little bit more careful because some things are not totally compact. So let's ignore this, and we get the section by the general procedure. And then when we have some birational modification and we consider the associated universal torsor and so on, actually everything will agree except this section. So as I was saying, that we just use this section to glue, and we show that it actually makes sense, because if we use any equivalence relation to glue, we may not get a polyhedral fan. But we can show that the gluing actually works out fine. So with a given phi, we get a convex cone, and then eventually by the gluing we obtain some rational polyhedral fan. So this is a rough idea for our generalization of this GKZ secondary fan. That's the first step. And the second step is about constructing a family over this space. So now let me, in the remaining few minutes, let me say something about the construction of our family, of this family of polarized Calabi-Yau pairs over this base, the toric variety of the secondary fan. So first, as I mentioned, that the construction is done in the first step by some affine family, by some affine mirror family. And for the affine mirror family, the base is this R, the monoid ring over the cone of curves. And the algebra a priori is just a module, R module with basis the integer points in the essential skeleton of U, and then the algebra structure, in other words, the structure constants, they are described by some counts of non-Archimedean disks. So these counts are really some kind of open Gromov-Witten counts that Tobias was explaining in the beginning of his lecture. And yeah, and all the heuristics about using these counts to get construction of mirror family really originated from Kontasevich homological mirror symmetry, and yeah, we tried, so people try to define, to study all these counts of curves with boundaries for the purpose of this construction. And here, yeah, as we have seen in Tobias' talk, that counts of curves with boundaries, it's a very complicated mathematical problem. So here, what we really want are structure constants really as numbers, not just fancier structures. Like in symplectic geometry, we have many theories about curve counting for curves with boundaries. But here, we are more interested in just getting genuine numbers out of these counts. So the strategy we have used based on my previous works is to study the counts in terms of non-Archimedean geometry. And since I don't have much time, I just show this picture. The structure constants for our mirror algebra is heuristically the number of holomorphic disks, but in the non-Archimedean sense, satisfying the following properties. So we want that its intersection number with the boundary is given by these pi, which are multiples of some boundary divisor. And then we ask that the boundary of the disk to map to this point Q, which is point in the skeleton, or point also seen as a point in the analytic space. And in non-Archimedean geometry, the boundary is a single point instead of a circle, and one can make sense of taking derivative at the boundary. And we ask the derivative to be equal to Q. And eventually we ask the class of this disk in a limiting sense to be gamma. So this is the heuristic for defining our mirror algebra. And in the last part, we will be extending this mirror algebra over our complete base, the complete toric variety. So for doing this, we do it in 4 steps, which I described in more detail in the notes, but maybe it's a bit too much detail to talk about it here. And when we do these steps, eventually what we get is extension to the, do I have, yeah, I have this summary theorem again. So eventually we do it, we extend little by little, and we eventually get a nice family over the complete toric variety. Thank you very much for your attention.
Thank you very much, Tony, for your talk. I give people 5 seconds to, all right, lower their hands in case they were applauses. And yes, is there any question? I have a silly question. Oh, Tom raised his hand.
My question is also pretty naive, but I just want to, could you say a bit more about exactly, here you, I'm looking at the bit where you were saying about using complex analytic geometry to count these disks and how that didn't work. Can you say a bit more about exactly what disks you're counting and why that doesn't work and why non-Archimedean geometry does help? Sorry, it's a big ask.
Yeah, thank you for the question. So really here, the idea about constructing the mirror variety using some kind of disk counts, it really originates from all the considerations of homological mirror symmetry. Because we know that in mirror symmetry, we have 2 big conjectures. One is the SYZ conjecture, another is the homological mirror symmetry conjecture. And then probably by the year 2000, Fukaya and also Maxime probably, and other symplectic geometers, they start to guess that combining this homological mirror symmetry conjecture and the SYZ conjecture, that we should be able to build some mirror manifolds using counts of some kind of disks, what they call Maslov index 0 disks, with boundaries on the Lagrangian torus fibers of the SYZ torus vibration. So this is the conjecture, but nobody really knows how to make it work, because they suggest that, or from the SYZ conjecture, it's suggested that we should build the mirror by counting these curves, and counting these curves will give so-called instanton corrections. But when we count these curves in complex geometry, we know that they are not deformation invariant. So it's exactly the phenomena explained in Tobias' talk just now, that, I mean, when we count closed curves, we see that the bad things, they are like codimension 2, as in Tobias' talk. But when we count curves with boundaries, then the moduli space has codimension, real codimension 1 boundary, and the numbers, they are just, we don't get numbers in general, unless we have other ways of, I mean, this is, people have all new ways of getting counts, but unfortunately, we get very nice structures, but we don't get numbers. So in non-Archimedean geometry, somehow we can get numbers, and we are using these numbers to do the job here from non-Archimedean geometry. Maybe you will ask why, like, what's the meaning of these numbers in the actual complex world? And I would like to think of non-Archimedean geometry as some kind of formulation to study these symplectic counts in some big limit. Maybe people say like large complex structure limit. Actually, I don't really know what it means, but it's some kind of limit of this SYZ vibration, and we are somehow using non-Archimedean geometry as like a mathematical framework to talk about these counts in some kind of limiting setting. And somehow in the limiting setting, this kind of dependence of these numbers, or this like phenomenon of things being not well defined, they disappear, and we can get genuine numbers. So it's really these genuine numbers that we employ for the construction.
Okay, thank you. That was really helpful. Thanks.
Thank you for the question.
Any more questions? I have a very naive question about unirationality. So if one looks at the moduli space of curves, there was this old unirationality conjecture for all genera that was eventually disproved at some point by Azimuth and Harris, I think. There was some Kodara dimension calculation that was performed in genus 23 or something. So in a sense, the question is unirationality, why is unirationality expected?
I mean, it's really, we are stating this because we don't need to introduce this complicated compactification, but essentially we are really conjecturing is really the compactified moduli space has some cover by toric variety. So then it's unirational, right? Because if you get the cover by toric variety, in particular, it is unirational.
Yeah, I completely agree with that. So the conjecture is in full generality when it comes to X. So X is just loop complex projective variety. There are no extra assumptions. Of course, you prove it for X of X in the cycle of.
But you need these things to exist, then it's quite a strong condition.
Right.
I think for higher genus curve, it doesn't. I think it doesn't fit here.
Right. Okay, thanks.
Yeah. This is so it's really something about Calabi-Yau, like log Calabi-Yau. So in one-dimensional case, maybe it's just a P1 with some points. Right. So hopefully they didn't contradict with what's known in the curve.
Okay, there are no more questions. Oh, Tom has a question.
One more. Sorry. Do you have any knowledge about the degree of this cover? Or, I mean, put another way, is this toric variety supposed to be parameterizing Calabi-Yaus with some extra structure or something like that?
Yeah, it's just some kind of what people call framing, or it's just a very tiny thing, such as fixing some isomorphism of a Picard lattice with some fixed lattice, just to remove some finite automorphism, this kind of things.
Okay, so you really could introduce some moduli space of framed Calabi-Yaus and say that this is a toric variety. That would be okay.
So in the two-dimensional case, I guess it's we really know how to introduce this extra structure, and then the group is then it's just a quotient by some finite group. I think in the literature maybe called a Weil group for this. Yeah, it's really this finite amount of data about some kind of automorphisms.
Of the Picard lattice.
Yes. Mm-hmm. So maybe you are right that if we can really figure out what extra thing to put, then it's a more beautiful, it will be a more beautiful statement that the moduli space of this thing plus this extra identification will just be a toric variety. Maybe that's better to state like this.
It's true, I don't know. Thanks.
Okay, there are no more questions. Let's thank Tony again.
Thank you.
And we resume at 1:45.